My name is Jackie Champagne, aka What a Merger Jr. So I am a first-year grad student here in the astronomy department at UT, and I recently moved here from the landfill of New Jersey to the literal surface of the sun. It's fine, I guess. Just kidding. Okay, so today I want to talk to you about how radio telescopes work and how specifically arrays of radio telescopes work. I am a huge radio nerd, and I hope by the end of this you are too. So before I get started, I think it's really important to put into context just how ridiculous a speaker you're about to listen to. So here's me. That's my nebula blanket, my ALMA mug, just one of many telescope mugs I own. This isn't my dog at all. I took this off of Facebook. But someday, when I'm not on a grad student salary, I will have that dog. And her name will be Jansky, after Carl Jansky. This is me at the Green Bank Telescope. This is the first time I got to see a radio telescope in real life. That's as close as I could get to it with my cell phone, since it's a radio telescope, but it's back here. I cried when I saw it. It was great. And this was my first science trip to a radio telescope. So my first month of grad school, my advisor flew me out to the Very Large Array in New Mexico. This is me on top of one of the dishes. So these things are 25 meters across and 5 meters high. No, not 5 meters, 5 stories. And it's all on ladders. It was an exercise to get to the top, but it was cool. Then when I was visiting grad schools, the department took us to visit the graffiti park in Austin, and I couldn't not tag my favorite telescope. And finally, this is a poorly photoshopped, not to scale photo of me on ALMA. Stay tuned for a real picture of me in Chile, but it hasn't happened yet. Okay, so most people, when they hear that I'm a radio astronomer, the first joke they make to me is, so you plug your headphones into it, right? And then you hear aliens. I wish it was that exciting, but actually it's more like this. Oh, these green circles actually denote real detections of 3 galaxies. I'll actually get to the real context of this image later. But it's more like sitting in a dark room and getting really excited when you see that. So here are some important people who were around for the beginning of radio astronomy. So radio astronomy is a fairly young science in terms of astronomy in general. So we have a long, rich history of classical optical astronomy that uses a refracting mirror telescope, like the kind that Galileo used, and all that kind of thing. But it wasn't until Maxwell proved his electromagnetic equations in the 1800s that we realized that electromagnetic fields could exist on a whole spectrum of wavelengths beyond what was visible. And around the 1930s, radio became widely used, especially in the military with radar and personal radios at home and stuff like that. And so then radio astronomy was born. So radio astronomy happened to be founded in my hell home state of New Jersey. Now, New Jersey is a 0 out of 10 state. Would not recommend to a friend. Unless you really like pizza or bagels or paying a lot of money to go onto a dirty beach. Or Bell Labs, which is what I'm about to tell you about. So this is Carl Jansky, and this is his buddy who has a German name that I can't say, of the last name Raber. And so Jansky and Raber were employees of Bell Labs. They were both trained as radio engineers, and they were working at Bell Telephone Laboratories in Holmdel, New Jersey. And in the 1930s, they built the first radio antenna, and they detected the first radio waves from space. So you can actually detect quite a lot in the radio, including thunderstorms and terrestrial phenomena. But they were getting this particular signal that showed up every 23 hours and 56 minutes, which is the length of a sidereal day, which meant that it was coming from somewhere, in the location of a star, basically. And what they were detecting actually was radio emission from Sag star, the supermassive black hole, the center of our galaxy. So that was the first radio detection in space. And then these guys down here are Penzias and Wilson, who also worked for Bell Labs. And later on, they were doing some stuff with NASA with their communication balloon satellite, something or other. And they built this horn antenna to be detecting microwave emission from these communication satellites. But they were getting this low level of noise in all their detections, no matter where they pointed their telescope, what time of day they were doing it, no matter the weather, and it was very strange and very frustrating. I don't know if you know this story, but I love this story. The next part of the story is someone told them to go check their horn antenna for bird shit. But bird shit it was not. Their signal persisted. Anyway, they were the first discoverers of the cosmic microwave background, which is the undulating leftover radiation from the Big Bang. And they received the Nobel Prize in Physics for that discovery. And then I hope you all know this guy, Carl Sagan. He popularized radio astronomy, especially with the Cosmos series and Contact, which I actually haven't seen. I'm the worst, but it's okay. Yeah, so you might have heard of the VLA and Arecibo from him. But radio astronomy in the last 10 to 15 years or so has really exploded, especially with the advent of these radio interferometers. ALMA is one of our newest facilities. It's my favorite telescope on the planet, if you haven't already figured that out. And this is FAST, currently the largest single-dish radio telescope on the planet. It was once Arecibo, but it's now FAST, the 500-meter aperture spherical telescope. It is being built in rural China, and it's just started taking its first observations. And then this down here is the VLA, which has been in operation since 1980, but was recently completely revamped and set up with whole new instruments. And so now the VLA is even more amazing than it was when it was built. So like I said, we're in something of a radio renaissance right now. And I'm going to tell you a little bit about what we can actually study in the radio besides Sag-A-Star. So what I mean by radio is this sort of lazy definition of anything longer than infrared. So it starts around 0.1 millimeters and goes out to the microwave, which is about a millimeter, and then radio, which is centimeter wavelengths and longer. And really the most important thing you can do with radio, at least according to me, because this is what I do, is studying invisible galaxies. So there's this important phenomenon that happens when stars are born, which is that they have these birth clouds that are very dusty. And it's basically like sands and silicates and things like that. And if you have a very active galaxy that has a lot of stars forming at one time, you get these massive dust clouds. And they're actually going to absorb the starlight altogether, which means that things like the Hubble Space Telescope are not going to see these galaxies at all, which hopefully spooks you a little bit, because that means that even our best space-based telescopes are missing like half the light in the universe, which is pretty scary. So yeah, we can study these invisible galaxies because what happens is the dust re-radiates the starlight in its thermal wavelength in the infrared and longer. So the submillimeter and the radio are really important detection methods for finding galaxies we didn't know were there before. And you can actually directly study this dust in the long wavelengths. And we can also study cold gas in the medium in between stars, so it's not just empty space out there. There are these gas clouds, and I'm going to get to that later. We can time precise clocks with pulsars. A lot of that is done with the NRAO. And then finally, there's the important concept of redshift, which is that things are moving away from us and the universe is expanding, which means that a mission that is coming from very far away is going to be a longer wavelength when you see it. And since luckily things aren't perpetually crashing into us, things aren't blue shifted, they're always red shifted most of the time. And radio is also really important for seeing things at really high redshift, like quasars and galaxies and galaxy clusters and stuff like that. So the main question that my science in particular tries to answer is, how did large-scale structure form in the universe? So blah, 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 dark matter, things are small at first and then they're larger. Trying to make this talk less long. Okay. All right. Yeah, Brendan stole my meme, but it's all right. So there are just 3 easy steps to making the perfect radio telescope. You too can do it. First step is you need to make yourself an antenna. And there are basically 2 classical ways to do this, but I mean, if you're really creative, you can think of another one. But most of the time, it's the spherical dish that you see. It's not a bowl. It's a satellite dish. And you can also use like wire antennas, like what's on top of a TV. But most of the time these days we use a dish that has a really large collecting area. And then the second thing you need is a receiver and an amplifier to actually record the voltages of your signals and turn it into something you can actually read. And then you're going to need to amplify it above your instrumental noise. One important thing about building a radio telescope is that because of thermal fluctuations, you need to keep your instruments very cool most of the time, so you need to house it in some kind of very cold gas. I think usually it's liquid nitrogen and liquid helium to keep things cold. And then finally, you need something to actually record your signal. So in the old days, it was something like the old EKGs where you had like an ink pen on graph paper. But now we typically use, digital signals, and a computer just directly reads it. And then if you're lucky, you get aliens. Okay, so you've built one telescope. Now, why not build a lot of telescopes? We run into this thing called the diffraction limit, which Brendan alluded to a little bit. And so basically this idea of angular resolution is that you need your telescope to be able to distinguish two different things as being discrete things. So this is a fairly intuitive concept because this is the way that eyes and cameras and things like that work. So, if you stood really far away from a forest, you would see a blur of green on top and brown on the bottom, but if you got closer, you'd be able to see that they're actually different objects, they're different trees, right? So there are two parameters that actually determine how well a telescope can distinguish things, and obviously we want to do that because we want to see that stars are different from planets and resolve two galaxies as separate from each other. So one thing is the wavelength that you're looking at, and the second is the diameter of the telescope that you're using. So imagine if you want to go from 1 micron to 1 millimeter, that's a factor of 1,000 in wavelength. So you need more or less a telescope that's 1,000 times larger. And as you can imagine, this presents some unique engineering and financial challenges because we can't really build a dish that's several hundred miles long. So luckily, physics saved us, and we can use an interferometer to do this. So really quick, the Reader's Digest version of this is that you have telescope 1 that is, or over here, that is separated by some spatial difference from telescope 2, and we're going to call that a baseline. Now, light is coming from your distant source, and it's all coming from the same source, but it's going to hit telescope 1 at some time, and it's going to hit telescope 2 at a slightly different time. And because we know the speed of light, it's fairly easy to track that time difference. And so really the only difference between your two telescopes is that there's a slight phase difference. So through a Fourier transform, you can go from two different signals from two different telescopes to a composite image. So basically what happens is you get a telescope that effectively has the same angular resolution as if you had built a telescope that is the diameter of this baseline. Now, the one problem is that you're not sampling this completely as if it was a full dish, right? So you're going to lose sensitivity as you make your baselines longer without putting anything in between. So once you've built many dishes that you want to put together into an array, you need to decide on the best configuration that preserves both your resolution and your sensitivity. To do this, a popular way is to have a compact array in the middle and then just sort of have this like nebulous cloud with varying baselines that go beyond that, like what ALMA does. But the VLA has always been in its classical Y shape, which throughout the year gets contracted and expanded, depending on the kind of object that you're trying to look at. So there's that way, and then the SKA is supposed to be some like spiral galaxy type thing. So pick some way to configure your telescopes, and then finally, you need to pick a place to put it. We have a problem with the atmosphere. Now, it's possible in the next 4 years we might not have an atmosphere anyway, so we might not need to worry about this anymore. But sorry, that's my one salty joke. So the problem with the atmosphere is that the Earth's atmosphere is going to absorb microwave emission. Because of the water vapor, it's just that sweet wavelength that it's going to absorb things. So you really don't want to put things in places with a lot of rainfall or things that are below sea level. Ideally, we put things in space, but the James Webb Space Telescope is already pretty big. It's close to 20 feet long, and we're talking about things that are 100 meters, so we just can't really launch it into space. So we do the best we can. There are some popular sites on Earth where you can do this, namely in desert climates and at really high altitude. So the Atacama Desert and the Andes Mountains in Chile are very popular. This is Kitt Peak Observatory. That's an optical telescope, but whatever. The point is that the Arizona mountains are really good. And they're the plains of the VLA. So when I went out there, I had no idea I was in the mountains because it's like the plains, but it's really high up. So that's a good place too. And then finally, Mauna Kea is a very popular place. It's a volcano on the Big Island in Hawaii, and there are a number of observatories there, but the most important is a submillimeter array. So That's the one I'm going to talk about real fast here. So this background image, this black blob, is an image of a galaxy taken by the Hubble Space Telescope. It's a starbursting galaxy at redshift 5. It's only about 1 kiloparsec long, which is about a 20th to a 30th of the size of the Milky Way. But it's forming stars at 1,000 solar masses per year, which is 1,000 times the rate of the Milky Way. So this thing is crazy active. But then these red contours are actually the ionized carbon emission from the SMA. So you can see that there's all this extended emission happening that the Hubble Space Telescope just completely missed. So that was something that I worked on in undergrad, and that was really cool. ALMA is amazing. And yeah, so there's all these wonderful new planets within the sun. Now, I don't know anything about planets, but this is a protoplanetary disk. It's called HL Tau, and this is the star. And then these lanes here are where baby planets are clearing out their orbits. So this was incredible. We were able to see actually, the birth of planets outside our solar system. So we know from Kepler that exoplanets are a thing, but this is just incredible to be able to resolve protoplanetary disks. But enough of things that I don't know about. This is a quasar. So quasars are basically highly energetic things that exist at all redshifts in the universe. They are probably emission coming from accretion disks of black holes. And some work I did in undergrad was looking at these quasars with ALMA, and ALMA was able to actually more than double the current catalog of quasars that we know exist. And this is at redshift 6. So that's only about 1 billion years after the Big Bang. And it's crazy that these things can be this bright and this obvious, because if you have something that bright, it's probably in a massive host galaxy. But at that redshift, it's almost impossible to get optical emission there. And so it's hard to study that. But I was doing work where in the continuum we can actually see galactic companions. So this thing over here is actually physically associated, which is a really cool discovery. One might even say it's all-amazing. Now, like I said, in 2011, the Very Large Array was rechristened and outfitted with a bunch of new instruments. Now, because we're not creative at all, we just add letters to acronyms. It was already the Very Large Array, and then they were like, Jansky was a person, let's put his name on it. So now it's the Jansky Very Large Array, but because we really just like to call things big, I personally decided to call it the Jumbo Very Large Array. So this is me next to the Ka band, which is the instrument that took these lovely images. So these are 3 dusty star-forming galaxies in the middle of a massive star-bursting protocluster at redshift 2.5. So basically, these are things that are still accreting mass, and these are prodigious star formers that are just crazy, crazy active. And we can actually find carbon monoxide coming out of these things. And carbon monoxide is a really important way to trace star formation. You go from carbon monoxide to molecular hydrogen, and from molecular hydrogen, you can actually determine how many stars are forming per year, which is like crazy cool. So in the future, protoclusters are basically expected to collapse into massive galaxy clusters, but we're watching them in their formation stage. So this is my first-year PhD project. But if you want to know about space, you got to know about the planets. And if you want to know about the planets, you got to listen to me right now. This is what's coming online in the future. Oh wait, this is my planet slide. Never mind, I can't make that joke yet. Okay. Yeah. So there are a couple of limitations to these telescopes, and so we're always trying to push the limit of what we know, and so we always want to build better instruments. And so there's one important thing. So like in 10 seconds or less, basically the reason we can see carbon monoxide is because it's a vibrational transition of the molecule, and that vibrational transition can happen at different energy levels in your atom, but the most important and accurate one to trace star formation is the ground state 1 to 0, 1. And then J just refers to how far up that ladder you're going. But ALMA, unfortunately, even though it's mi corazón, mi alma, can't actually see the really low J ones. And so we would want something that is as good as ALMA, but for lower J. And then we're also missing the sensitivity with the VLA to do a complete census of all the molecular gas in the universe, because, we're lucky if we resolve it into a couple of pixels. But it would be really cool to resolve total kinematics for those things. And then finally, we just always want to be able to probe deeper and deeper redshifts so we can actually witness the epoch of reionization. So one thing that's coming online is the square kilometre array. Yep. I'm not going to talk too much about this. I really don't know anything about it. I just want to make that joke. But you heard it here first, folks. The next generation VLA is coming down the pipeline, hopefully, maybe. So really the crux of this talk is that radio telescopes are still on the horizon. We're still building bigger and better ones. So for some reason in Contact, we went from the 27 actual antennas that exist there to like hundreds. I don't know why, but I guess in the future we were able to build hundreds of dishes. But this might actually happen. So with the next generation VLA, we hope to build a lot more telescopes, get these baselines way, way longer to hundreds of kilometers, and just build the biggest, best telescope that has ever existed. We're still in the baby stages of planning this thing. Like, we really know nothing. I can't even show you proof of concept, like, imagine this kind of things. But hopefully, like, give it 20 years or so, maybe you'll actually hear about this thing being built. So I just wanted to give you a sneak peek of that. Okay, now pretend I just made that planets joke. So some other things that we want to keep doing with radio telescopes are imaging the terrestrial zones of young planets around protoplanetary disks. We always want to be doing ISM physics, which is what I care about, so that's the interstellar medium, and learn more about star formation on the scale of a single cloud. So a single cloud can be as low as 50 parsecs or so. And then obviously this complete sensitive cold molecular gas would be really, really exciting to do. So just as a last, what if we could do this thing? This is an example of something we'd like to do with the NGVLA. So this is CO emission from a model galaxy at redshift 2. And in only 40 hours, the NGVLA, in theory, would be able to get this image out of this actual thing from a simulation. So hopefully, it would be super, super cool if we could actually do this. But scientists are still putting their noggins together, trying to come up with how to build this thing. Is that the end? Yeah. OK, so hopefully you understand now why I'm a radio head. Yeah, anyway, so thank you very much for listening. If you have any questions, I'd be happy to take them. Thank you.
All right. Okay, question right up front. You, sir?
Well,
why do you hate New Jersey so much? Not exactly a science question, but we're going to find out.
It's the armpit of America. It's smelly. We have bad traffic. The people are obnoxious. But I do really miss Chinese food, to be honest with you.
All right, in the back. New Jersey defense or a question? Yep. Right, you in the orange.
That's a great question. Yeah, so the question is, how do you distinguish things that are actually sources from space and not fluctuations in the atmosphere? Yeah, so that's actually something that requires, well, okay. So if you do spectroscopy and you get spectral lines, there are certain things that are real physical sources that will coincide with things that we know come from the atmosphere. So unfortunately, at certain bandwidths, you kind of just have to throw it out altogether. So I don't know. There's some deal where you can like fit a Gaussian to the atmosphere and like subtract it. But I don't know anything about that. But my partner who works, well, not my life partner, my like academic partner who also works for my advisor knows all about that. So ask. I don't know if he has a name, but it's Patrick. Go ask him.
Okay. Next question. You, sir.
Could you repeat that? Sorry. Right. So the question was, do you actually physically get to go to the telescopes for observing, or do you dial it in and do it remotely? Unfortunately, well, fortunately, there's the technological advancement that remote observing is quite common now. And for ALMA in particular, there's a technical team that does all the observing. So you send them your proposal and you're like, these are my sources, please go look at it. And then a few months later, it just happens and they send it to you. They're like, we did your observations. But I would prefer it if I could go to Chile and see this thing. But, you know, whatever.
All right, one more in the back, sir.
Yeah. Oh. With dark matter,
yeah. Is there a suggestion of radio observation becomes more like fluid matter, or is it still a separation?
Right. So the question is about dark matter and how radio observations allow us to basically test it, right? To test the collapse of baryonic matter. So cold dark matter simulations suggest that things go from the bottom up. So you get small things at first, like some stars and like a single galaxy, and then at later times you get things that are in galaxy clusters and then superclusters. So basically, you wouldn't expect to see a supercluster at really high redshift. If you do hot dark matter, it suggests the opposite, that things are one large structure in the beginning and then collapse. I don't know. They fragment into smaller things at later times. But radio observations of things like dusty star-forming galaxies, which we couldn't see in other wavelengths, confirm that the protoclusters are earlier times, and the galaxy clusters themselves that have virialized altogether, they definitely don't happen until later times. So that's basically the confirmation that we have.
All right, let's thank What Emerges Junior one more time.